Hi everybody, this is Sandeep Giri here, and we will start the session in 15 minutes. Any communication you want to do, you can do using Q&A application. Okay, so I'll be responding to your questions from here. Okay, see if Yevgen is asking that when the webinar will be started. It is going to start in 11 minutes. Okay. So the actual session will start in 11 minutes. I'm just welcoming all the guests right now. Hi Evgen, this is Sandeep Giri here. I'll be the instructor for this class. And this class is going to start in 10 minutes now. And all of you feel free to introduce yourself using the Q&A app. Okay. You can ask any communication you have to do will have to go through this Q&A app. Are you able to use it? It'll be great if you guys introduce yourself uh, by the way of asking a question. So, because that's the only way possible in Google Hangout on air. So the way we work is that for the first session, which is public and in which all the guests are invited, we use Google Hangout on air. While when it's a private session, we can we involve everybody in the class. Okay, where everybody can chat and everything. So because in Google Hangout there can be at most 10 participants at a time. That is why I've kept it a Google Google Hangout on air in which everybody is a viewer. So please ask your questions. Are you able to ask your questions? And in case you are not, just let me know on this number. Basically, I'll just put my number here. Okay, so my email ID is sandeep at nobigdata.com. Okay, so you can you know in case you get stuck somewhere, just drop me an email here. I'll immediately take a reply. Okay, and my personal email ID is that. Okay, okay. So I think this will be sufficient. Just drop me an email. I immediately reply. Okay, and hi Hari, how are you? Welcome to the session. And hello everybody, please introduce yourself by the way of asking questions using Q&A app. Hello everybody. Hi Jamil. And probably, so you are working with United Health Group as a solution architect on J2EE platform. So are you located in Mumbai? Hello, Santosh. Welcome to the session. Hi, Yevgen. Welcome to the session. Which country are you from, Yevgen? It'll be great if you introduce yourself the way Jamil has introduced, telling a bit of background and which uh, company they're working for, if that is all right for you. Hi, Harinder. Welcome to the class. Harinder is from CSC Noida. Hi, Lohita. Welcome to the class. So Yevgen is from support engineer and okay, and we have, yes, Santosh, proceed with your question. Hello, Santosh and Chandresh. So Jamil is logged in from Delhi. That's great. Great to know about you, Yevgen. You are with the VoIP company. That's interesting because VoIP is the problem we face most of the time. Hi, Lohita. Welcome to the session. Hi, so basically the way you will see the video is through the sort of, you can switch between the past and the live, whatever you want to do during the broadcast itself. And you will be asking questions using Q&A app. So feel free to ask the questions. Hi, Piyush Patel. Welcome to the session. Yevgen is from Ukraine. Interesting. Okay. So hello everybody again, because there are all new joinees are there in the session. So yes, Santosh, this Santosh's question is this video will be available in the future? Yes, Santosh, this will be available to all the attendees in this class. Okay. This will be an unlisted video, but it will be only available to the attendees of the class, and it will be up to you whether you want to share this video with other people or not. So Lohita says that she is working with CSC. Great to know about you, Lohita, and welcome to the class. Again, welcome everybody. To ask questions, use Q&A application, and to communicate anything to me, you that also you communicate through the Q&A app. Hi, Ashish. Ashish is from Pune. Ashish Barot, and welcome to the class, Ashish. And thank you for coming. It is great to have you in the class. Little bit of more introduction will be needed. Good evening, everybody. This is Sandeep Giri here. Now it's 8:30. We are starting the session now, and um, I would like to again those who have not introduced yet. I would like themselves to introduce. And the way these sessions happen is that the first session is over Google Hangout, and rest of the sessions are using other mechanisms because we expect more viewers. That is why we do not keep it on normal Hangout. So we keep it on Google Hangout on air. So feel free to ask questions as much as you can using Q&A app and communicate using that one. Hi Sachin Kakkar. So Sachin is from again United Health Group. Welcome to the class, Sachin. Looking forward to more questions from your side. Hi Santosh. Santosh Subali and Chandresh both are from Pune. Great, 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 great. Okay, okay. So let's start with the class. It's already 1 minute over, and I think for first 5 minutes, if anybody has not introduced himself, please introduce themselves. It will be great, and that way, because in future you might be a part of the session. It'll be easier. Jignesh Vasoya says hello to everybody, and Sachin also says hello to everybody, and then okay. So if you have not introduced yourself, please feel free to introduce yourself. It will be great. And after the class also, if you have any doubts, you can, ping me and ask me. Okay. And so for first 5 minutes, I would like to run the introductory session. 8:35, we start with big data and Hadoop session. Okay. Okay. Santosh Subali says hello to everybody. So we have 11 viewers as of now. Great, great, great. Feel free to ask your questions using Q&A app and click on the live button. Click on the live button which is there while you are watching it through YouTube. You can click on live button and then you will jump to the live. And ask your questions using Q&A app. And when you join the class, feel free to introduce yourself. It is great to introduce yourself before starting the class. Okay, okay. So this session is about big data and Hadoop. Okay. This is an introductory session, though second half will dive into details of the architecture of Hadoop. Okay. So the format these sessions work is that we broadcast these over Google Hangout on air, in which only selected people can watch it, those who have signed up for the session. It's not public Hangout. And in this session, you ask your questions using Q&A app. And okay, you ask your questions using Q&A app. I answer all of your questions at the end of every slide. Okay. So right now there are no questions. I am proceeding forward. Good evening, everybody. I am Sandeep Giri. I am your instructor for Big Data and Hadoop introductory session. And welcome to No Big Data Sessions. These sessions are basically mostly on the big data technologies, and we have an expertise board on big data. Most of our guys are from Google and Amazon, and most of us have been working on big data technologies for quite some time. And the unique selling proposition we have with respect to no big data is that we interact a lot, ask a lot of questions. We provide lifetime access to the content. For example, the video of this class will be available to you forever. And then we have set up our own servers, a cloud on which you will be doing all of your experiments. Instead of worrying about where will I get all that servers from, we provide around 10 to 15 computers cluster on which you will be doing an experiments. And basically the whole class will have the access to the cluster, so that they don't have to worry about arranging the hardware. Some people have Windows hardware, other have Mac. All they have to do is just connect to our cluster and start. Then we provide a 24-hour support. Then we provide 24/7 support, meaning that anytime you get stuck somewhere, just drop us an email or give us a call if something is urgent. So you are stuck with respect to a particular assignment which we have given, or you are not able to access to our servers, or there is some problem, difficulty, you have got stuck, and you have somehow arranged this time to solve our assignment or work. So you can call us at any point of time, and we will be more than happy to help you. And so this is about the full course. Okay, these are the features we provide in the full course. This session is the first session of that full course out of 10 sessions. And we provide a real life project at the end of the project session. So that has to be submitted within 15 days of the completion of the project. Then we have quizzes and a certification test. We provide our own certificate so that you can put it on your LinkedIn profile, and also you can we give you a testimony based on your performance in this test. This recommendation or testimony is given on LinkedIn, so that you can put it on so that it is visible to your professional network. And these are 10 classes, 3 hours each, And we also help people conduct their mock interviews. Okay, so you finished a class with us and you are still worried that you will not be able to, crack the interviews on big data and all, or any of the topics. So what we have done is we have connected with the industry and arranged the mock interviewers, and in which we connect both the people, the interviewer and interviewee, over again Google Hangout or GoToMeeting face to face, and they can have the discussions. Okay, and whatever format they prefer, we do that. So the overall objective is to help people enhance their career and improve their knowledge regarding big data. Let me have a look at the question answer session. So Santosh's question is, what is required configuration of laptop to install? So Santosh, first, do not worry about the installations, because we would provide you a complete cluster online. All you have to do is install SSH clients such as PuTTY, so that you can connect to our servers through that. So you have to install PuTTY, and that's all. No matter what your configuration laptop configuration is, I am sure PuTTY will run on it. Or if you are on Mac or Linux, you will have SSH installed by default. So nothing to worry on that front. Also, if you want to install, you can install at your wish. Okay. So it is up to you, but there is not much of a hardware requirement from the side of Hadoop. Okay, we'll talk about it after first session. Now, hello Ishan. Ishan is from Dell. Welcome Ishan for the session. Hi Rahul. Rahul is from HCL Technologies, and welcome Rahul for the session. So before I proceed, do you have any questions right now? I doubt that. Okay. So my background is a bit that I joined DE Shaw in 2002. That time also I was working on very large data section, because at DE Shaw we had terabytes of data at that point of time itself. So I was working on anti-money laundering, whereby we used to check whether any of the transaction in the history of our organization is is a terrorist or something. So in that we had to do a lot of data churning to figure out whether an individual is listed on any of the government websites as the illegal entity. So that time itself, I was working on a cluster where we had thousands of computers on which we used to submit our jobs and then get it done. That time the big data word was not coined. Then I started Tbits Global in 2006, built a enterprise product and built a document management system for lots of power companies and so on. And then in Mobi I joined later in the beginning of 2012, and built a recommender system which required a churning of 2200 terabytes. So this was the biggest data encounter I had at that point of time. Okay, where I had to, based on 200 terabytes of the web server logs. Logs are the history records of the website access. So based on that, I was doing a recommendation for them, which was really thrilling project, and we were able to do it. Later I joined Amazon. At Amazon, I was doing a lot of data engineering with respect to image manipulations, and we had at Amazon we had all sorts of infrastructure for, like, we had Hadoop and we had other kind of machine learning environment. And the beautiful part of Hadoop is that even Amazon has adopted it. Okay, so I was working on in-house similar systems. Basically they have taken Hadoop and they have customized it for themselves. So And then this year after March, I started knowbigdata.com for giving professional trainings. So this is about me. So feel free to ask me any question, and I am more than happy to explain the concepts, even if it's very simple concept. If you think it's a really stupid question, still ask that question, because no question I have found so far is irrelevant or stupid. Okay. So feel free to ask your questions, and that is the whole objective of these classes. There are hundreds of classes online videos, recorded videos, which you can watch. But the problem with all of those videos is, in the beginning itself, if you get a doubt, then for you, the whole of the video will be blacked out. Okay. So clear the doubt here also before it gets blacked out for you. The whole thing will become, useless if you do not ask your doubts. Okay, so let me have a look at the question answer. Sachin is saying that not able to connect to this webinar. Sachin, this is the way it works. You should be able to see this. Okay, click on the live button. You should be able to see this live. Okay, and this is how it works. So you ask all your questions using Q&A app, and that's it. So great. So there are no other questions, and yeah. Rahul is saying that no questions, you may proceed. Okay, great, great. So that was all about me. I was trying to flaunt my skills, and yeah, I will try my best not to flaunt it again. And all right. So in this session, today we are going to discuss the general concept about big data, and then we will dive into details about Hadoop architecture. Okay. So this session is going to be little soft in the beginning, it is going to be little hard at the end. Okay, so stay tuned. Stay tuned. In today's session, we will talk about what is big data and all of these topics. So let's skip it. Let's move ahead. Okay. So, okay. So how many of us know actually what is a big data? And give a quick definition they have. Anybody? Okay, okay. So somebody is not able to join the session because it doesn't work in IE. The QA app doesn't work in IE. Hi Anurag. Nice. So you are finally able to use this. Great. Great. So okay. So let me describe what is big data. Big data is simply, you know, data of very big size which you cannot use your existing tools. Okay. When you are trying to process that data, you are not able to use your existing tools to solve your problem. Okay. So maybe that, the existing data you are able to store, but you are not able to process. Then we start calling it big data, as simple as that. Okay. The word is very vague, and it's like an adjective when we say this person is rich. Okay, and the way rich has no, a connotation, there is no specific limit of that one. Similarly, big data has no specific boundaries. The only way we define big data is the moment the data is big enough that you cannot use your traditional tools to handle it. And that's when we realize that, oh, this problem is of big data, is a big data problem. Okay. Okay. So Amit Sachan is saying that big data is any kind of unstructured data which is of big size. Yes. So, so the data does not necessarily need to be unstructured. It can be structured also. It can be structured also. And structured data also get big and to a point that you can't handle with your existing tool. Yes, Jamil is right. Jamil has exactly answered that question. And great. Big data such amount of that cannot be handled by one computer. That's also very good answer, Yevgen. And great, great. So Anurag Singh is a little late, but let me introduce him. He is from CSC and he had just joined in. Probably he is from Noida. Yes, he's from Noida. And then right. So some of us really know what exactly is big data. Okay. So this is the simple definition. So when you hit a point of time where your single computer is not able to handle that amount of data, or your traditional tools are not able to handle your data, you start calling it big data. And more important than the definition of big data is knowing what are the tools in industry are there to handle it. Okay, so what I'm going to do is there are a couple of definitions. Why I'm telling you these definitions? Because people might ask you. So IBM came up with a funky definition saying first they said three V's, then later said four V's. Okay, and just to sound a little technical, so four V's that describe big data is volume, which means the data which is stored already you have that data. Okay, Facebook has a lot of data per day and you have that data stored in the disk somewhere. That is called the volume. And then velocity. Velocity is like when you have built a solution which requires a lot of updates and clicks and all sorts of pings from the user. So these pings, updates are coming in the form of data and that you need to handle. That's called the velocity of the data, at what rate this data is coming in. And then variety. Earlier, all of our systems, few years back, all of our systems were designed to keep the transactions or bank transactions in mind. That was one of the very beginning goals of having a data storage. And at that point of time, people did not think too much about the multimedia data or the maps or other new kind of data structure which evolve. So nowadays we have all sorts of data such as videos, audio, pictures, and then 3D maps, and then graphs of people, graph representing people, or just binary files which need to be stored on a large scale, like say think of Google Drive. Google Drive is providing the space to the whole world. Now Google Drive can contain all sorts of data in it. So these are all characterized as variety of data. Then you have veracity of data, where you are not sure whether some of this data may be useless or may be useful, and there are inconsistencies in that data. That is called veracity. Okay. And forget about, I mean they themselves don't know what does a veracity actually means. They try to say that the result of one data is called veracity, and other time there is inconsistency. So these are like verbiage. So all these four V, volume, velocity, variety, and veracity, is nice to know word. Okay, when you are talking to the people. Now let me just jump in. So I hope people don't have question. Okay. Hey Anurag Singh, welcome to the class again. And Anurag is working with CSC as an application architect. Anurag, there will be a live button. Why don't you come back to the main one, to the live session? Lohita, this is how we connect to the session. Okay. So what kind of errors are you getting? Could you just drop me an email? Because this is how we connect. The way you have asked the question, this is how we connect to the session. You click on live button and you will be live. Hi Ijaz, welcome to the class. You are a little late. So, I mean, still, please introduce yourself. Okay. So I'm moving on. Perfect. Harendra has given a perfect definition. Big data refers to the massive amount of data that are difficult to analyze and handle using common database tools. So probably Harendra is little running behind. I've just dropped him a message. Okay, now let's move on to the next. Now enough with the verbiage. Now let's move on to something important. So this is a introductory question. So how many bytes are there in petabytes? Quick answers. So how many bytes are there in petabytes? I'm waiting for your answers. How many bytes are there in petabytes? That will help me understand who are my candidates. Or I think, okay, I'm just waiting for the first answer. First. Okay. So, yes. So, great. Let me just move. So, everybody got the answer from Google, searching on Google. Okay. So, 10 to the power 15. Yeah, close to that one. Great. So, everybody has got an answer. So, Yevgen, no. It's not 2 to the power 15. 2 to the power 15 is very small as compared to 10 to the power 15. Okay. 2 to the power 15 means 15 bits. Okay. So let me introduce Kamal Upadhyay. Kamal is from Redbus, and he's a silent observer till now. And he says the petabyte is 10 to the 15. Good, good, good. So almost everybody got an answer. Why I have asked this is because people will keep on talking in PB, and PB is petabyte. And when you think about petabyte, think about 15 zeros after 10, that many bytes. Or you can better correlate this way. So kilo, mega, giga, tera, peta, exa, zeta, and iota. And tera we know, right? Tera is 1024 gigabytes, and peta is 1024 terabytes. Okay. So that's how it is. Now let's have a look at this screen. Why big data now? So at the beginning of 2002, when the internet started flourishing fast, the data started exploding. It is as simple as that. Earlier, the data, when we computed the data, it was either CDs or tape drives or cassettes or sort of records, and those kind of things we considered data, or the banking data. And that was very small. Though we had data, but it was in analog form. In 1986, for example, it was 2.6 exabytes, and exabyte is how much? You can see 1024 petabytes. Okay. So 2.6 estimated exabytes in analog and point zero 0.02 exabytes in digital. So what we are saying here is that we had 20 petabytes data in digital at that point of time. And 20 petabytes is nothing as of today. Okay. 20 petabytes is 20,000 1 terabyte hard disk. Okay. And in today's time, even a one cluster of a small hosting service will have that many space. So that was the digital data in 1986. The growth of that data, digital data, rose very slowly up to 1993. And after 1993, when the internet started becoming public, the data took a little bit of more pace. And in 2002, when the digital era was actually starting, the data started exploding. In 2002, somebody did a survey, and they say that digital data is 280 exabytes. Digital data is 280 exabyte. In this diagram, this color, the color which is down is the digital storage, and the color above is an analog storage. So analog storage is decreasing while digital storage has just exploded. Exploded is the word. So as of today, the estimated in 2002, 2007, the the uh, the data was 280 exabytes estimated. Okay, so this is to give you a feel that the world data is actually exploding. Reason being that we have found a way to store this data. We have the storage have become cheaper. People have become more connected, and I will come back to that again. Now, now what exactly, when we talked about there's so much of data and this and that. Now, what exactly is the problem associated with the big data? Okay, okay. So Santosh is asking me to make the presentation full screen. The problem with making full screen is that I'm not able to see your questions quickly, and that is why I'm avoiding it. Okay. Hi Vishnu, and he's saying hi to all of the attendees. Okay, okay. So we talked about the data. Yes, Ashish Bharat is right. That's a nice way to represent. And great, 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 great. So Izaz is having some difficulty in connecting to the session. So Izaz, I would say that um, I mean I will not be able to help much right away. But if you send me an email saying this is where I may help. Okay. And the reason why we are doing it on Google Hangout is that our the failure rate on other softwares are very high. I've tried Google GoToMeeting, I've tried WebEx, but the failure rate is too high. At least 1 out of 10 person will be not be able to join it at all. Okay, so let me try to make it full screen as can I? How do you go to next slide? I don't know. Okay. I'm trying, actually people are having difficulties in seeing this, so I'm trying to um, show you. Great, great. See. Oh, oh, and never mind. I'll just stick with what I was doing. Okay, I'm sorry. I'm sorry. I was trying to make it a full screen. Never mind. I'll just stick to it. So, so Vishnu is just joining in. Vishnu is from Chandigarh and works as full-time freelancer on Ruby on Rail, which is MVC-based open source platform. Welcome, Vishnu, and we'll love to get connected later point of time. And this is nice to meet you. Okay. So I'm sorry, guys, I'm not able to make that full screen. Never mind. So so when the data is big, when the data is huge, what are the things that become bottleneck? At one point or the another, one of these four things will become your bottleneck. First one is CPU. Second is your RAM. RAM is the computer memory which we use for the processing mostly. Third is your disk size. So RAM, when we say RAM, it means three things: speed, size, and uh, bus size, data bus size. You might keep on increasing your RAM and you might keep on increasing your CPU, but the data bus becomes the bottleneck. And then we have a disk size. So disk size is at most 1 terabyte or 2 terabytes and that sort. And the price starts increasing very high if you try to go for a above disks. And the other thing with respect to disk is the speed of the disk, the rate at which you can read or write. That is why people have invented SSD. Okay. The other factor which comes from the using so many disks is the rate of failure of a disk is very, very, very high. Okay. If you have 100 you have 100 disks, at least one will fail today. Okay. So that is the statistics with respect to the normal hard disk drives. Then fourth is the network. You might store your data somewhere, and when you want to process, you will have to transfer that data first from the network to your disk, and then from disk to your RAM, and back and forth. So the network also becomes a bottleneck. So these are the four problems associated with big data. So maybe today your data doesn't look like big because you are not doing much of a processing or much of a transfer at a regular period of time. Tomorrow, when you have to do further processing, any of these four things might become your constraints. So those are the main bottlenecks when you are handling big data. At least one of these are going to fail. So Harender is not able to listen anything. Are you guys able to hear clearly? Okay, so let me just move on. Let me ask you, if you have 100 terabyte of movies, how would you store it? How would you store 100 terabyte movies? Hello? So are you guys able to hear me? Okay, so at least one person is able to hear me. So I'm thinking that it's not my problem. So Harinder, just check with your audio or try to reconnect. Okay, there might be some problem somewhere. So if you have 100 terabyte of data, if you have 100 terabyte of data, how are you going to store it? I'm waiting for your answers. The moment I get the first answer, I'll move on. Remember that remember that the normal NAS or anything you purchase, they generally give you 10 terabyte, 20 terabytes. Okay. And we are talking about a real data, which you have to access. And say you are building a videos network and you want to store your all videos in this database, this terabyte size. How are you going to store them such that you can access any content at any point of time? So basically, Rahul and Ashish Bharat are saying that you could have a storage array of 100 terabyte, or maybe Yevgen is saying that NAS or a few RAIDs. Anybody else? Hari is saying that you can use SAN storage. Interesting, interesting. Okay. Now let's say that do you know the price of NAS or SAN? Do you know how much does it cost and how much maximum do they give you? Great, great. So almost everybody is able to hear me clearly. Okay, so I've got an interesting answer from Amit. He says that we can store it on Cassandra nodes. So yes, it's a good answer. But okay, now I've got an interesting answer from Jamil. So this is what I was looking for. To store 100 terabyte of data, we can store it in distributed file system. And as data grows further, we can have more hard disk in horizontal scaled fashion. Yes, yes. So this is what I'm going to describe how. So Anurag says that if data is so high that so I'm not aware of how to store so much data. Yes. So Ashish is saying we store these things on NAS and SAN. Yes, that's interesting idea. But the thing is that it is little costly. And if the data grows further to 10,000 terabytes or 20,000 terabytes, then you will get into a bit of a problem. Yes. So Yevgen says that we can use Hadoop and a lot of servers with commodity hardware. That's the point. So Ishan says store it on a shared storage over cluster of disks. That's also possible. Now I'll just, all of these things are actually uh, either the part of the solution or the problem which I'm going to pose further. So have 100 terabyte of data, 1 TB drives and make 100 subfolders and mount these in a single folder somewhere. So all you did was you did a network attached storage as people suggested and connected these 100 terabytes in the network, and on the entry server what you did was you made a folder with respect to each of these drive and mounted these 100 into those 100 folders. Now when the user looks at it, he sees a single folder containing 100 folders in which you can store the data. Okay, now what are the challenges associated with it? There are various kind of challenges associated with this approach which I just described. This approach, the one which I'm talking here, this one, has got some problems. First, as we talked, the hard disk drives or any drives have a horrible failover. Every hard disk crashes every third year or fourth year, and some hard disks start crashing in the first year itself. So you need to have failovers. Failover means, I mean, we don't only need a backup, but also need a failover. Backup means we are taking the backup of the data, and failover means it quickly swaps between the two. Okay. And how would you distribute? The second problem which occurs is, say we have 100 of such drives, we are pretty happy, and we created a scheme that all the movies starting with A will go to the first machine, movies starting with B go to the second one, and so on. Now suddenly what we realize is the servers which we have dedicated for Q are empty because there is hardly any movie with Q. So, and that's where the problem starts. So that some of the servers are overloaded and others are free. So the data is not uniformly loaded, distributed with a manual kind of distribution. Third one is this the best value for money? In your organization, there will be some 200 GB hard disk lying there, some 100 GB, some 500 GB, and all sorts of up to 8 GB you will find in your organization. So are you using the right resources? 1 TB hard disks are extremely costly. The lower ones are very cheap per GB. So do you want this? Ideally, your solution should be such that no matter how many hard disk drive we have, we should be able to connect it as a single place. And how do we do that? If we connect too many drives, then managing it by creating folders and folders, it becomes very impossible game to play. If you have like 2000 drives and you have to manage them, mounting and everything, it becomes horrible task. And when you have data, so the application guys will not be able to store things properly, because they will have to be told your data, if your movie starts with A, then put it here. Now the fifth point is, what about increasing the accessibility? Say all of your friends want to watch the same movie. Okay, so now one of the servers on which that movie stored is overloaded, while all of your 99 servers are free. So what will happen? None of the people will be able to watch a movie because server will crash. And this is where a lot of people have invented really beautiful solutions, such as splitting a movie and spreading over 100 servers, so that all of these 100 people are able to watch it simultaneously using these cluster of servers. Okay, so Rahul is saying that $4 per GB is the cost. Yes, in their setup. Great. Now, if you see this, now what exactly is the solution for this kind of automatic management? Like at Amazon, we had like infinite space for us to store anything related to the website, Amazon website. And we never had to fiddle around with the folders, subfolders, never. All we were given that this is the place where you store your data, no matter whether it's terabyte or 100 terabyte or whatever it is, we will be able to store it. And that is when the systems like HDFS or Hadoop distributed file system come into play. They abstract you out from all of this management and give you an enormous amount of increased accessibility. Okay, so my next problem which I'm going to pose, this one, first one was related to the storage. How do you store the data? Okay, so the solution I have told you is HDFS, Hadoop Distributed File System. Basically a way where we divide a file and distribute across the network, and you get the actual file. You don't have to worry about slicing and dicing. You don't have to worry about that. The system is already doing it for you. Now next question is about how do you process data. So when we talk about processing, almost all processing problems can be broken into sorting the data. Almost all. If we are not able to break a problem into sorting the data, then we are in a really tough scenario. Specifically the problems with respect to the map search, they are not easily solvable with using sorting. Say for example, when we say group by or when we say order by, we are using the sort of the database. Or when we are creating an index on a table, what exactly we are doing? We are creating sort. We are sorting that column's values and creating indexes. So sorting remains as the baseline for all the systems, and that is why I am posing this problem to you. If you have a 1 gigahertz processor, how do you sort 1 terabyte of data? Or let me present 1 terabyte of data in a different manner. You have 100 byte size names of people who have 100 characters in them, and there are 100 such people. Okay, sorry, there are 10 billion such people with 100 bytes name. How do you sort their names? How do you order their names in decreasing or ascending order, whatever you prefer? So any processing mostly can be converted into sorting, whether it's where clause when you are searching in the index, or where you are doing group by or order by or joining the two data sets. All of these are actually sorting problems. So how do you sort? How much time do you think 1 gigahertz processor will take to do 1 terabyte of data? As a process, let me explain to you. The way you sort the data is, you can only sort the data how much you can keep in one memory at a time. So what you do is you divide 1 terabyte of data, and imagine that you have say 4 GB RAM. Imagine that you have 4 GB RAM at a time. So what you do is you slice this 1 terabyte data into 4 GB small chunks and sort these 4 GB chunks, and then you merge all of those together. And imagine how much time would it take? Give me a rough estimate. Give me a rough estimate. Let's say when we call this, we say 1 TB equals, and we are saying 10 million names of names having 10 million names having 100 characters each. So basically all we are trying to do is, how do you sort 10 billion strings? Or I mean, I'm not asking you the approach, how fast can you do that? Okay, and the RAM is, say you have RAM equals, say 2 GB, just for the, how much time do you think it is going to take? Yevgen is saying that hours or probably a day. Do you think it is going to take a day or hours? I mean, I'm posing this question to you. First, sorting is the baseline of all data processing and data churning. Whether it's where clause when we are trying to filter the data or search the data, because we create indexes, that is a sorting problem. Second, we do order by, that's a sorting problem. Then we do joins, that's a sorting problem. So you sort one and then merge with other one. Internally it's a sorting problem. And group by is internally a sorting problem. So almost all the database operations which are intensive are sorting problem. If your query does not, I mean, is slow, it might be because in the traditional systems, it might be because you have not created sufficient indexes. But in case of big data, the problem arises even you cannot create even the indexes on that size of data. Okay, so Rahul is saying break the data into smaller parts, allot different cores or to sort the data parallelly. That is on single machine. Okay, that is your on single machine. But imagine doing it on a, I mean, even if you have 4 cores, we are talking about one single core here. Okay, we are talking about single core here. So yes, let me get back to the, so as per my estimation and the things which I have run, the best time I have got so far, best, this is not average, this is the best time I have got, is 5 hours. Okay, now 5 hours is not good enough. Okay, why I have posed this question? Because our assumption is that computer is super fast. Okay, everything it does in milliseconds or seconds. But when it comes to a terabyte of data, no matter which algorithm you use to sort it, you will not be able to go above 5 hours. Okay, and you might go, I mean, You cannot improve your algorithm beyond a certain time. So what you need to do, either you increase the hardware, you put more cores into it, or you spread out. You have 100 machines, let 100 machine parallelly sort your data, right? Let me tell you. For example, Google on 8 September 2011 said they sorted 10,000 terabyte of data using 8,000 computers, and it took hardly 6.5 hours. Okay, and we are talking about 1 terabyte of data here. Okay, now the other problem with the current systems is that if the data goes to 10 terabyte, it will not be 50 hours. It will be far beyond it. It is not linear relation that 1 terabyte took 5 hours, so 10 terabyte will take 50 hours. No, it will take maybe 100 hours. Okay, so there is no linear relation between the two. And then other 4 factors we talked about earlier will hit you badly. And that's when the problem with respect to big data starts. You are running a SQL query, or you are running an insert, for example. An insert will result in resorting the data, or insertion, or other game. So insert query for 1 terabyte data, it starts taking 3 hours of your time, then you are gone for a toss. Okay, so that is why, or when you are searching, or when you are indexing a table column, if it takes a 10 hours or 12 hours of your time, then this solution is not workable for you. Imagine that you are running an e-commerce site like Amazon, and your one single insert, just because the user has placed an order, has taken say 1 hour. Is it acceptable? No. So that is when you start looking out for various kinds of solutions. So Jamil is saying this is a typical use case of MapReduce. Map works on small chunks which eventually generate. Thank you, Jamil. This is what I am trying to actually explain. Okay. Thank you for that. And you are a little step ahead. Yeah, these are the great stats from Google, Rahul. Thank you. And we need to do all of this all the time. And when you are running any company, 1 terabyte data is nothing. 1 terabyte data you will get in couple of hours. If you are running a simple service, a telephone directory which is open to the worldwide, 1 terabyte data you'll get very quickly. Okay, so churning of the data becomes a problem the moment you go public, the moment you open it as a service to the worldwide. Gone are the days when you used to create a service for 1,000 users. You create a service as of today for 10 million users or a billion users, or and when you say concurrent users, earlier we used to talk about 10 concurrent users. Now we talk about 1,000 concurrent users or 10,000 concurrent users, and we call that concurrent users as TPS. Okay, transactions per second. So, and that's when the problem starts. And this is important now. Why did this happen? Why did we have to sort terabyte data? First, connectivity between things and the people, and people and the people. Second, the smartphones. Everybody has got a smartphone, and that is generating data at every minute. I'm right now getting lots of SMS, lots of, I mean, those SMS are being synced to somewhere. Any photo I take, that is being synced somewhere. And any call I make is, I record that call. So all of this is happening concurrently. Okay. And that's why, and smartphone, I keep on forwarding the things. So I'm generating a lot of data. For example, my call records is around 400 MB. Why? Because I have not deleted a single call record since 2007. Okay, so my point is that every minute or every second we are creating lot of data. And other thing why this is more important, Moore's law, which was saying that every 6 months we will have twice memory and twice processing power, which failed pathetically in 2009 or 2008, I don't remember. So because the data bus became the bottleneck and we could not put more registers onto the chip, and we stopped making faster processors, all we are doing is put more core into a processor, put more cores into that. Okay, we are not making faster processors anymore. Putting more cores means put more processors into a single processor. So Moore's law failed and we got so much of connectivity, and we got this smartphone which is also well connected and which is has all the sort of sensors in it, which generates a lot of data internally for you, that I mean you the whole data is actually exploding at a very fast pace. Now let's talk about uh, in the B2B world where we have enterprises, what sort of big data are we talking about? And here some numbers, if you see, those small numbers you may not be able to see probably. So 4.6 billion mobile phones connections are there right now as of today. And as we are speaking, there billions of users are connected to the internet. And on Facebook, there are 1 billion monthly active users. And every month, 30 billion, billion has 9 zeros in it. Okay, 30 billion pieces shared monthly. Pieces as in some people are chatting, some people are sending messages, some people are resharing a particular quote or resharing a photo and all that sort of thing. And similarly, Twitter says that they have 175 million tweets every day. That's a huge data. Few years ago, nobody had thought about it. Before 2000, this was just imaginary. And in the enterprise world, as of today, everybody needs a big data solution. Okay. For the retailing, like for Amazon, what we were doing is starting from the user behavior analysis. For example, we give the suggestions to the people. People like you also bought these things. People who bought this product also bought this. And we at Amazon we used to crawl half of the internet and figure out what people are talking about Amazon. And based on this whole data, we were able to figure out that there is something wrong with our services, and this was a great thing to do. And the other than recommendation engines, what we do is a search quality. Search quality as in when you type in a word, we give all sorts of searches. Okay. And so other is that credit card frauds. We detect credit card frauds very frequently. All of those, Amazon is already doing it, while the rest of the world is still yet to catch up. Those people who have been into physical market, they have not come up with these kind of techniques yet. People are doing, they are moving fast. Like Flipkart has moved fast. They have started doing all of this. And then telecommunications. Customer churn prevention, as in why people are leaving us, why the network is slow. While calling data record, if these people can give me a suggestion based on my past calling behavior that you should be taking this plan, it will be a great thing for the user. And analyzing the network, that in the night this network is active, so we need to put more people this side. So all the sort of thing are possible if they are able to handle the big data. They need to, if they start recording each and every activity of the customers, they will be able to provide a better experience to the customers. Similarly, these are few other examples such as fraud detection, and we had Aadhaar card. Aadhaar card has its cluster and all. Similarly, there are in healthcare, lots of people are working. I was just reading about how Hadoop was being used in various kinds of gene sequencing. The problems which supercomputers could not solve earlier, now things like Hadoop and the distributed computing is taming and is actually really, really helpful to them. And I mean, earlier we used to think that we need supercomputer for these things, but people have figured out that supercomputer is not coming. So build yourself a system where we can use thousands and millions of computers parallelly. Okay. Let me have a look at questions. So no questions on this anyway. Let me get back. And more customers. These are some very, very simple and obvious customers. At InMobi, what we were doing, we were actually at InMobi, we were just giving the ads to people. Say you are playing a game, the ad that comes, there are high chances that it is coming from InMobi. Okay, that's all InMobi does. It shows the ads to people. It shows the ad in apps. And there we had a terabyte data being generated just by the logs of our web server every day. Okay, so even such a simple system where we were just showing an ad is a big data problem. In a traditional scheme, what people used to do is just take this Apache log, either delete it after 10 days or just put it somewhere. Had we deleted at InMobi, had we deleted this past history of the users, we would not have been successful at all. Okay, say for example, at InMobi, what we were doing, at any moment of time, our people will ask, hey, how many users are coming from this particular geography in this duration? If we had no background history, we will not be able to answer such question, and hence our business goes down. And so the moment, since the businesses have realized that you need to store such humongous data, whether we process now or later, that's a total different question. Now the world has started looking out for a solution, and hence the people for providing this solution. Now these are some of the, this ugly slide because it has too many names in it. You have Yahoo, Facebook, LinkedIn, and all sorts of examples in front of us who are actually using solution like Hadoop, day in, day out. Their life depends on this. And UHC also, United Health, is also a good user now. I was discussing with them because some of us are from UHC. So this is about the big data and where it is. Now the rest of the session is about Hadoop. There are multiple solutions to the big data problems, such as your NoSQL databases. And NoSQL databases are something like MongoDB, something like Cassandra, and other smaller solutions. But the one which does the justice as the big data solution, which does the justice to the name big data solutions, is Hadoop, because Hadoop has got the whole architecture in place. Okay. So before I proceed, I would love to answer your questions. Do you have any questions right now for me? Either you guys have slept off or I am expecting or I'm so great that I'm able to explain everything? I think it's that people have slept off. So do you guys have any questions before I move to Hadoop session? Okay. Well, great. Now all the questions have come in a single shot. Okay, great. So, so people have not slept off. People are asking questions, and I've got some interesting questions from Santosh Bali. So Santosh is asking where we cannot use big data. I mean, data size is big and we still cannot use it. Mm. So Santosh's question is that even if the data size is big, why cannot use the big data? So see, big data is not a solution per se. Big data is the keyword characterizing the data is big, that we could not do that. Maybe your question is that what are the problems in which these approaches like Hadoop and other these solutions like Hadoop and other scenarios are not useful. Okay. So anywhere, if you are, do not expect at all your data is going to grow beyond a certain, say you are a bank, and even if half of the country becomes your customer, then also if your data is not your transactional data specifically, if that doesn't grow beyond a certain size, transactional data as in what is the current state of affairs, not the background log. Okay. So if that doesn't grow beyond a limit, right, then you are good to go. You don't need this kind of scenario. Okay. But this generally kind of thought saying that we don't need a big data solution for these kind of scenario is generally a lack of vision. For example, a bank deletes my transaction history after 2 years or 3 years of time. Okay, this is not acceptable in today's world. Imagine Gmail deleting your email after 3 years of time. Gmail does not. Earlier people used to do that. So most of the people think that their solution does not need a kind of big data approach, but it is just their lack of vision. And the scenarios which you should ought not to use a big data solution is heavily transactional information, where redundancy or distributed computing might lead to a little bit inconsistency. Okay. So Jamil's question is really interesting. He says that most of the Hadoop use cases I have come across are offline data analysis, right? Are there any use case for online processing, or even it makes sense to do it online processing using Hadoop? So Jamil, this was a design decision which was taken by Hadoop long back. Okay. And it was basically inspiration from Google, because Google was also just pitching for the offline ones. And for online data processing, they were using other kind of tools. But recently, Apache has started a project called Spark, okay, whose objective is to give the make the online processing possible using Hadoop. And also, since Hadoop has moved on to the new architecture called Yarn, which makes it possible to use Hadoop for even your very fast turnaround time. Okay, so it is nowadays possible to use Hadoop along with the Spark in case of a real-time processing. Okay, earlier it was generally batch processing. Interesting question. Thank you. Okay, moving on. So what exactly is Hadoop? Hadoop is a cute little yellow toy elephant the founder's kid was playing around with, after which he kept the name. It's a framework to handle big data, the big data which we characterize. So basically, Hadoop is a distributed programming framework where we utilize thousands of computers to do your job. Your job could be processing or storage. Okay. It is open source. Open source means that if you want to make a change in it, it is possible. It's not, a magic. If you are really interested, you can just check out the code and review the code. And it is as simple as that. And that has changed the way people think about the software. I have made contribution to Cassandra earlier. So the thing is that if you don't like something, either you contribute or fork. Fork as in make a copy of Hadoop and start. And that gives a great peace of mind to the enterprises in the adoption of Hadoop. Okay, and that is the reason that the world has adopted such a solution at such a fast pace. Even Linux has been adopted for the exact same reasons. Android is laid on top of Linux, and being open source made it possible that the research of one person is benefiting other people, and there are more researchers coming up because they are able to learn from each other's way of thinking, and way of thinking is represented in the code. So open source has changed the way we used to look at the product, and hence when had the Hadoop not been open source, I wouldn't have been teaching you Hadoop. Okay, it would be somebody's property, and they will be charging you a hand and leg just for the training. Okay, so and they'll be charging you for the books. There will be all sorts of things, the way Microsoft used to do earlier. And that is what changed everything, to an extent that Amazon is forced to build a platform to run Apache Hadoop cluster. Everybody supports it. Almost every hosting provider is bound to support it. And there are 3 companies who provide you a good support, such as Cloudera and Hortonworks. They provide you a complete support on Hadoop. So it is open source and well supported. In case your organization need a dedicated support, you can hire them, but they are very, very costly. Then it is basically reliable, scalable, and distributed computing. So if you want to do your distributed computing, where you utilize thousands of computers and solve a problem, or store data, then this is a solution for you. This was created by a guy called Dog Cutting, and then Mike Caffarella joined him. They were building a search engine called Notch. So they built this, and this both the components were inspired from Google's paper. Google did not release an open source project, but they published a paper on how to build a distributed platform, and that's what laid the complete base for Hadoop. Okay. And it was written in Java so that almost every hardware you can connect together. So Java runs almost on all platforms. Okay. Whether inside browser, outside browser, on phone, on your old Nokia phone and your Motorola phone, everywhere. So, and even in fridge, and some microwave oven have Java. So they created the Hadoop in Java so that you can connect all of these devices together, and installing such a thing is easier. So let me repeat Anurag Singh's question. Anurag Singh has got a question before I move on to the next slide. Whether big data solution is useful, or there is any scope for big data solutions in batch processing as well. Okay, okay. So yes, so batch processing is actually what Hadoop was doing till date. When we say big data solution, right now I'm talking about Hadoop. So once, I mean, Hadoop is actually, when people say big data solution, it's generally we call it, are you building it on Hadoop? Okay, this is how the world actually works right now. So big data solution is useful, or there any scope for big data solution in batch processing? Yes. So Hadoop was actually built for batch processing. Okay. Now we have gone forward for the online transaction processing as well, but it has been basically built for batch processing. So it is useful, the big data solution is useful for the batch processing. That's what I mean to say. Now, the core of Hadoop, let me just discuss, and at 10 o'clock we take a break for 5 to 10 minutes. Okay. Now we discussed about what exactly is Hadoop and how it is useful. And now I'm going to delve a little bit inside Hadoop. What are the various key components of Hadoop are? So as per the Hadoop themselves, they have splitted the Hadoop into three basic utilities, three basic components. One is common utilities. Common utilities as in the normal code, the normal utilities which all of our other products depend upon. So you would not need to know about Hadoop common utilities right now. Okay, they are for other projects. Now the basic core component of Hadoop are HDFS and MapReduce engine. So I posed two problems. One was storing 100 terabyte of data. The other was sorting 1 terabyte of data. Okay. So these two problems are what is being solved by these two solutions. HDFS helps you store your data using multiple hard disks on multiple computers. Okay. And MapReduce engine divides takes the code from you, executes it on hundreds of nodes parallelly, and return you the result. So instead of bringing data from multiple computers to a central place and executing code, the code moves to the data and that's where it executes, because in case the data has to be moved, 1 terabyte of data over network will take couple of hours for the movement itself. Okay, while sorting will take lesser time. So no matter what your network is, 1 terabyte data will still be huge transfer cost. So what Hadoop guys did, just you are looking for to sort something or looking for a needle in a haystack. For that you don't need to carry the haystack to the needle. You just take the needle to the haystack and do the processing at the haystack itself. So that's what MapReduce did. MapReduce gave you a programming paradigm such that you can write your logic in such a way that it can be distributed parallelly without you worrying about your distribution. All you have to do is think in terms of map and reduce. Okay. So that is what MapReduce engine gave you. So so these are the two base components we are going to talk about. One is HDFS, which is Hadoop distributed file system, and we will tell you the dynamics of how actually the Hadoop file system works. How does it create redundancy? Say you are thinking that this particular piece of data is very important to you, and you want 3 replicas of it. Even if 2 hard disks crash, then also you save your data. That kind of redundancy. And how does Hadoop does it? And how does it use multiple hard disks? Because hard disk reading speed also becomes a concern to you, and that is when if you are trying to read all the people are trying to read from the same machine, it becomes problematic. And those are the kind of problems HDFS solved. I will come back to it again in the detail after the architecture. So these are the basic 3 sections of Hadoop. One is common utilities, which HDFS and MapReduce internally use. And then we have HDFS, which helps you store humongous or big data. MapReduce engine makes it possible to break your logic such that it can be distributed without you worrying about how will I combine the data or how will I run my logic on multiple machines. So this is the core of Hadoop. And this is the architecture I am going to talk about. So we are going to take a break of so break for 10 minutes. Okay, guys, are you there? Or so I'm going to take a 10 minutes break. We will come back at 10:10. Okay, and we'll to carry it further. Okay. Thank you very much. I'm not closing this webcast. I'll just mute my microphone. Hi guys, I'm back. Hi guys, I'm back. Great, great. So Amit is back, Ashish is back, and awesome. So let's start. I hope you guys are not getting bored. And so we were talking about, just a second. Great. We were talking about the various components in which are involved in Hadoop. So the basic components which are involved in Hadoop are HDFS, which is this, okay, and MapReduce. Okay, this is not related to you mostly. Okay, most these are the two things which define. First is storage, other is compute engine. These are the two things which you would require as a from our perspective. These are the two problems we were trying to solve. First was how do we store 100 terabyte data? Otherwise, how do we sort 1 terabyte data? Okay, so storing is solved by HDFS and computation is solved by MapReduce. And Hadoop Commons is basically nothing but a set of utilities which MapReduce and HDFS use internally. Now let's talk about components. Okay, so after these basic components, there is a whole ecosystem of things. So the base and the heart of everything, where all the data is going to lie, is your HDFS. The one that is in blue. So this is the HDFS. Okay. Then the second level, which we talk about, is your, so that's the base. Everything is going to get stored there and going to get read from there. Now the second level which comes is your MapReduce compute engine. Okay. MapReduce basically divides your logic and distributes on machines, while HDFS divides your storage files and puts into various machines and gives you back as a single file. And MapReduce does the same thing with your logic. You write your logic, MapReduce will take it and execute it on multiple machines closer to the data you are trying to churn, and then will give you an output. And then comes HBase. So there is a philosophy called NoSQL databases. NoSQL databases are those databases which do not have database tables in them. Okay, those which do not follow, are not able to follow the ACID properties of a transaction, which is because of distributing the data all across the network. So in simpler words, HBase internally uses MapReduce as well as HDFS to give you a facility of quick, sort of a database facility. It looks like a database table where you can insert data, update data, and do where clause and select clause, but it internally is storing on HDFS, and for the churning it is using the MapReduce logic. So every time you do a query, it hands it over to MapReduce and then gives back you data, or it does its own kind of key value pair lookups. So that those are the things which HBase does for you. HBase is a database provided by this ecosystem which sits on top of HDFS and in the MapReduce zone. Okay. internally it uses both MapReduce as well as the HDFS. Okay. Okay. So I think there is a lag in questions. So I just got Izaz is saying welcome back, and Ashish was already here, and Ishan has started. Great. And okay, so we are all here. Nobody is sleeping. I'm happy to know that. And so Ashish has got a good question. He says that does HDFS use object read method to store data? So so I mean, let me first answer his question regarding the HBase stores object in the RAID. Let me, I missed out your answer. Just a second, give me a minute. Does HDFS use object RAID method to store data? I have not sure what does the object RAID method to store data mean. I might have to figure that out. And basically HDFS, I'll come back to the architecture very quickly. It is a very interesting question. Thank you for that question. I'll come back to that in a minute. Okay. Okay. So Amit is saying HBase can be replaced with other databases. Yes, you can replace that. So if effectively like solutions like Cassandra, if you tell them that start storing the data in HDFS, they will start storing the data in HDFS. They have got a driver for storing this database. And there was one more question from somebody which says that can the question was that can you store into some other database or query some other database using HBase? I mean, the answer is no, but using Hive we can do that. I'll explain to you later in the next slides. Okay, great. Now let's say, so we described the compute engine in rough. So this rest of the session will go about talking about HDFS in detail, and then we'll talk about compute engine, which is MapReduce. So MapReduce, Yarn, and compute engine are, you know, I'm going to use them interchangeably. Okay, though there is a bit of difference, but never mind. So and MapReduce, so you write your code. Code can be written using Python, Java, and other languages like Ruby on Rails, and you hand over this code to Hadoop, saying this is my code, and run it all across. Or your code can also be written in JavaScript and hand it over to Hadoop, saying this function is what I call map, this function which what I call reduce, and now run them and give me the output. Map and reduce, I'm going to dedicate a separate session for map and reduce, and in which I'll give you a hands-on, I'll describe in detail, but for now just understand this, that by the way of creating map and reduce functions, you are able to send your code to multiple machines simultaneously and get it executed and get the results correctly. Okay, and in a very simple form, you can take an analogy that you are writing a group by clause. Group by has two sections. One is selection of the ID. On what IDs are you doing a group by? That is done by your map function, where you define that this is my ID out of this data. And then group by defines what are the aggregations are you going to do on each of the IDs as selected by group by clause. And that aggregation might be sum, might be average, might be anything. is defined in terms of reduce functions. You can write your own functions in using your code. So basically, map and reduce is actually a reflection of your group by clause. Okay. If you don't have a map, you only have a reduce. That means you are doing a group by on all, which is generally not the case. But you might have a map, but you might not have a reduce, which means you did a group by, but you are not aggregating data. Okay, which is equivalent to a select statement. Okay, never mind. Just understand that MapReduce, the job of a MapReduce is to run your logic parallelly on multiple machines and give you the output. So the code travels to various machines in the network and does the job, and you get the output. Okay. So that is the compute engine's role. Now on the top of these sit first is your Hive. Hive is nothing but an SQL interface. This SQL interface is beautiful in the sense that it helps you query your data. Okay, it helps you query your data using an SQL like syntax, and internally every time you are doing SQL, it's actually converting that into a MapReduce job and executing it parallelly all across the systems and giving you the result. And the other beautiful part of Hive is that you can use it as a single interface to connect to multiple systems. Whether it's Cassandra, MongoDB, or a flat file system, XML, you can use Hive as a single point of entry and then join the data from your other databases with the data which is lying in HBase. So, or in the file system. So Hive, other than being an SQL interface to HBase and your file system, it also helps you combining your data with the other databases you might have in your organization. So that is why you would need to learn Hive when we talk about big data, because none of the big data solutions are going to exist in isolation. Half of your data is going to stay in your traditional systems, while the bigger data is going to go in a Hadoop like cluster. Or maybe if you have an object kind of storage, you want to store objects and you don't want to store in a flat file system, then you might need a MongoDB kind of solution. Or if you are trying to store a sort of a map of people or graph of people, then you might need a different kind of a database. So inevitably, in an organization, you will end up using multiple kind of databases, and this data will have to be combined together to give you desired output. And that is where Hive comes into picture. Hive gives you a single interface to combine this data together and query this data together. So while querying, you write along with the table name, select star from this table, and in the bracket you write using this driver, and under the driver you also write which server, all the server URL. So using it gives you a syntax with which you can query multiple servers at a single time, multiple databases, multiple kind of databases. So everybody is giving a driver of Hive to the public, saying now you can use our database using Hive, and that is the power of Hive. Okay, Hive acts really like a beautiful interface to all of this. Okay. I've got a very good question. So Jamil is asking, since data is stored in HDFS, do we use HBase as a client to pull out the data which is stored in HDFS? No and yes. So it is up to you. If you stored your data using HBase, then you pull out the data using HBase only. Okay. The file will be stored in HDFS. The way the data is going to be divided is in the HDFS. So, but when you're querying, you should be querying using HBase. But other than that, you can directly interact with HDFS, just like the way you interact with the file system. Copy this data there, give, delete this file, and give me this data. I want to cat this file. I mean, cat. If you are aware of Unix, then the cat command means that you are typing, printing the data onto the screen. So you can do all of that directly. So if you have a Hadoop client installed, or after this class you will be installing it, you might install it. So you can do a Hadoop DFS, LS, or cat, or something like that, and then that client will talk to the Hadoop HDFS and get you the desired file. Okay. So basically, you can directly interact with the file system. I hope I answered your question, Jamil. Great. Now let's move on to the next screen. Not really, not next screen. I'll just move on to the, let's say, pig Latin. Okay. So a couple of researchers found that we could write more efficient query using a newer language as compared to SQL. Okay. So they came up, I mean, if you know Brian, if you know Kernighan, who built a C programming language, he came up with a new language at Google for querying a data which is lying in a distributed system, and instead of writing MapReduce job for everything, you could write your queries using a language called Pig Latin. It's named as something else at Google, but the guys at Hadoop, they took those specifications and wrote a similar tool called Pig, in which you define that this is my variable, which is basically the way, if you guys remember, we write select query, select star from this, and we assign it a name, and then you can use this as a set and then do other churning. Okay, so that's a set based, very strictly set based query language, similar to SQL, but a little different paradigm, which makes it more efficient to query to query on a distributed file system. And under the hood, whether you are writing your query using Hive, that logic is internally getting converted into your Java classes, into a code which is MapReduce. Whether you are using Hive or Pig, internally it gets converted into Java code, and which gets sent to all the nodes, and you get the result. So these are the two things which are very similar. While Hive is strictly like SQL, select star from blah blah blah, while Pig Latin is a different set based, similar to SQL, it's a different language. So what you do is, first you define A equals select star from blah. So A is one set. Now do select star from A, join it with B, and then you do other churning. So at the end of this, when you will always execute this whole Pig Latin in a conjunction. Okay, so it is a set based operation language which you will have to learn, and this is actually very efficient as compared to SQL. I find it very interesting and useful. And so you will always have this question in mind, whether to use SQL or use Pig Latin. My suggestion is learn Pig Latin, because it is going to immensely improve the performance. Okay, because SQL was not written with respect to keeping this kind of environment in mind, where the data will be stored on multiple servers and you will be doing all this computing. While the Pig Latin has been written bottom up, keeping in mind that all your logic is going to get converted into MapReduce, and you should not be writing the code for everything. Okay, because for MapReduce you will have to write your logic in the code. So being a DBA, you need to understand both the language, or being a developer, you need to understand both the language so that you can generate reports or generate the outcome using either of these three tools. So I talked about MapReduce, which is the base tool, then SQL interface, which sits on top of it, top of MapReduce, and then Pig, which also sits on top of MapReduce. So every time you write a script using uh, SQL interface, which is Hive or Pig, it get converted into MapReduce logic, and then it's sent across to the network. So Amit Sachan is saying that execution of queries is offline or online. So what does that mean? See, basically, for you, the query doesn't end unless you get the data. It might take some time, but it will get you data. Okay, it will show you that okay, I'm creating this MapReduce, and under the hood it will start sending all of this data all across, and it will be online in the sense that the code will not, the SQL will not finish until you get the output. Okay, in that sense it is online. While in case of MapReduce, what you do is you send the code, and generally you forget about it. It executes in parallel, it stores your result somewhere, and then informs you the task is finished. So I hope I answered your question, Amit. So in case of Pigletin or Hive, the answers you will get is generally online. Okay, are online, not generally online. While when you are writing your MapReduce, it's up to you how you stitch your logic. Do you want to wait for the code to finish, or do you just want to forget after scheduling it? And that's exactly the role of Oozie. Oozie is a workflow system which makes it possible to stitch together various kind of tasks on your Hadoop. So you define the whole workflow, that this is going to get executed, then this is going to get executed, and the data from here to comes to here, and that is the role of Oozie. I have used Azagban as well. That was the role of, before Oozie, we had Azkaban in place of that. So these are the workflow where we define in a format, in sort of a declarative language, saying this is what I want to do in this step, and then next one, then next one, and say this is my big task, this is my MapReduce, this is my Hive. So all of this you can combine together in a single script and get it executed on Oozie. Okay, now let's talk about a very interesting tool which came along. Let's talk about some interesting tool called Mahout. Mahout is actually what it means. The way Mahout is somebody who drives an elephant or who rides an elephant. The owner of the elephant. Okay. So they tame it, they control it and all that. So similarly, Mahout is something which does the statistical analysis for you, and very complicated task, it makes it very simple for you. Take the case of recommendation engine. If you are able to form a recommendation, is what? Based on your past history, I am suggesting you something, or based on your context, I am suggesting you something. All of those kind of tasks have been become simple, have become very simple, that you don't have to write extra lines of code for that. Okay. And Mahout does it on both levels. First is statistical analysis, and second is machine learning. So both these tasks, both these kind of tasks which you want to do on top of your on top of your data, is made very simple and possible using Mahout, and it is worth learning Mahout. I will not be covering it too much in this session, but I will be going through a couple of basic examples in not in this session, in the course. I'll be going through a couple of basic examples with Mahout, while I'll be going full throttle with Hive and Pig along with the workflow. I'll be describing in one session each of these. Mahout, I Mahout itself will take maybe 4 sessions, which is 12 hours to describe fully. So I will stick to couple of basic examples. If you want to do, you can go for a full-fledged course on Mahout. Okay, or you can do it for yourself, but I'll be starting a course on Mahout and data sciences later point of time. So whatever you need as a developer, you will get in these sessions on Mahout. And on top of it sits the user. Either user directly talks to Uzi, and then Uzi talks to the whole platform, or the user is talking to writing code in using Java, Python, or directly writing commands, and they talking to any of these platforms. So even user can directly talk to HDFS here. Okay, user can basically directly talk to the user to the platform. Okay, directly to the HDFS, right? And similarly, user can directly talk to MapReduce also. Basically, they write the code and hand it over using but that will be done using Java, Python, or any of other JavaScript kind of languages. So this is what is the whole stack is about. So Kamal's question is that are they from Apache itself? So basically they are not from Apache, it's just that they lie under the umbrella called Apache. So people develop these products, and then Apache, the team from Apache evaluates them and their terms and condition, and then they get affiliated with a particular component. So all of these are related to Apache Mahout actually, as per them. Okay, so Apache is more like a licensing. People develop it and then get it reviewed with Apache guys. If the product is really good, they accept it, and then it is featured under Apache name. Okay, so this is what it is. When I say main component is this. Okay, and I forgot to mention couple of guys who might get angry. So there is a tool called Flume. Flume takes your plain text and other files and helps you import that into HDFS. And then you have Scoop, which takes the structured data and pushes it into HBase or HDFS. Okay, so these are the two tools which are sort of ETL. ETL is extract, transform, and load kind of tools which help you uh, pushing the unstructured and structured data into the HDFS. And before, so I think I have described what is unstructured and what is structured. Structured is something where we don't have to parse it. Parsing does not require too much of an effort. It's very strictly we are able to I mean your code is quickly able to access a particular variable from the whole data. Similar or your code actually knows that what part lies where in the data. While unstructured is something like a plain text or something like a image, for which loading the data would require enormous amount of computing. Not enormous, but it will require enough of computing and would require time. So that is what is, I mean, photos and your tweets and plain text files and the image maps, All of these are called unstructured data, while the data in the database is called structured, and the things are in which are in XML are called semi-structured. Semi-structured. Great. Now into details. I'll be diving into details of the Hadoop file system. Okay. So before I move on to that, I would like to answer your questions. So Jamil's question is, as a Hadoop developer, which are the frameworks from Hadoop systems I should concentrate on? Hadoop Core, HBase, Hive, Oozie. So all of these you should know very well. And HDFS and MapReduce you should inevitably learn. Even if you are, you have not done programming for quite some time and you are out of touch, then also I strongly recommend that you should try out at least a simple logic with MapReduce. A simple code you should look at. I will give an example, maybe in the another class, not today. Today I'm not going to cover MapReduce, and I have a separate class video uploaded for the MapReduce, which actually describes the simple paradigm. And so HDFS, yes. MapReduce, yes. HBase you cannot avoid. Hive, yes. Oozie, yes. And you are forgetting the piglet in here. So all of these components you should work, and the order should be the way I have described. Starting from HDFS, then MapReduce, little bit MapReduce, not really, you need not to master it, all need to know the paradigm. Okay, if you are a programmer, then you have to master the MapReduce. Okay. Okay. And then HBase, yes, you might need. Hive, you don't need to learn much because it is basically SQL. You will need to just understand a bit of query differences. Oozie will be very small task for you, but you are actually missed Pig and Mahout. Pig is very much interesting and useful. Okay. In certain circumstances, when your Hive queries are performing very bad, your Pig queries will be very fast. Okay. And it's worth to know, but almost all of those tasks you can do using Hive or MapReduce. Okay. And Oozie also is like secondary. So order of preference is exactly in the manner you have written. I am just adding on the tail Pig and Mahout. What happened? Why the sharing has gone? Okay. So Kamal's question is, so there is a probable issue of compatibility. Yes, when we are talking about Hive and it's talking about other queries, then yes, there is a probable issue of compatibility. Okay, you are talking in terms of Apache itself. Okay, okay. Why this sharing is getting disabled again and again? There might be compatibility issues, not between the Hadoop components in the internal, but with the other databases. So all of these, since all of these live on top of HDFS, none of them can afford a compatibility issue at all. So there cannot be a compatibility issue between MapReduce and HDFS. Okay. So do not worry about that. So when Hadoop is actually adopting these products, they adopt only based on that it is belonging to the Hadoop architecture. They don't just take a database from MySQL and have put it here. No, it's actually built bottom up with the people uh, from the from the open source world. So it's not something like acquisition. Okay. Okay. So now moving on. Core of Hadoop is first is HDFS, which is Hadoop Distributed File System. So data is distributed across the nodes. It's heavily fault tolerant and has a high throughput. High throughput. The reason for both is that each file first is splitted. Okay, and each file is stored in these nodes, and each piece of the file has is replicated and put across 2 machines or 3 machines based on your replication factor. So first, that makes it fault tolerant. If one machine goes down, your same piece is existing in another machine. Second, high throughput, meaning if two persons are asking for the same piece, you can give from one machine, first person from first machine and second person from the second machine, because you have kept it at 2 places. Also, if 100 people are accessing the same file but at a different location, say 100 people are watching a video, same video, but one person is watching from is at 0th second, other is at the 5th second, and third one is the 15th second, and so on. There are hundreds of such people. So they will be actually accessing different servers, different nodes of your distributed file system. Okay, so that is the beauty of distributing the file across the network. So in a fixed size chunk, it splits it and replicates it and puts it into various machines, and there is a name node. The work of the name node is splitting and sending it to every machine, and also keep a track of which name is stored where. And since there is no specification, we are not storing too big a piece on a machine. We are storing say 64 MB of chunk on each machine, which means that low cost hardware is also good to go, which means that your mobile can also be another node because it has 8 GB of data, 8 GB of SD card. So low cost hardware, meaning even if you have an old machine which has 8 GB, you can use that one. And MapReduce splits the task across the computer, across the processors, or across the nodes, and code travels to the data, not the vice versa. It is self-healing, and self-healing in the sense that in case it was executing on a machine, one of the copy of your code went to a machine, it got shut down. Okay, now you have another machine with similar data, it will be sent to that machine. That is called self-healing. And so and these are the design objectives of while designing MapReduce. Similarly, MapReduce was built obviously for the clustered storage. And in case of MapReduce, there is something called job tracker. Similar to NameNode, there is a job tracker which manages what is being executed where. This diagram, if you see, it shows you 5 boxes. Okay, this one, the first one, it says job tracker, and under that you say admin node or name node. So let's first talk about HDFS cluster. In case of HDFS cluster, say you have 5 machines. One of the machines you will make it admin node or name node, while rest of the machines will be the data node. Okay, so whenever you are trying to store a file, you are talking to the name node. Name node is directing your driver or the software driver through which you are connecting, and it's directing the driver to store the file in separate data node. So a data node is the actual storage, while name node is generally only the metadata on top of these chunks. Meaning, if you are trying to store a 1 terabyte of file, or say you have got a Blu-ray which is 80 GB. So first the chunk went to these data nodes. This is metadata. This information, which chunk went to which data node, is the metadata which name node tracks. Similarly, in case of MapReduce, you have one leader called JobTracker. You submit your job to JobTracker. JobTracker makes a copy of your MapReduce logic and sends it to the task trackers. Task trackers are the real executor of the logic, and the task tracker is also a data node, which means the data is there. On the top of that data, you are trying to do the churning. Okay, so all of these task trackers will do your job, give back the results to task tracker and job tracker, and job tracker will give back to you. This is how it works. The whole architecture is sort of a master slave. There are multiple masters in case of HDFS there are multiple slaves in case of HDFS cluster. These slaves are called data nodes. Similarly, in case of MapReduce, the slaves called data nodes also run a service called task tracker, whose job is to run your task. Okay. So Ashish Barot's question is, what is the minimum size of chunk in which data is written on nodes? 64K or less? So, I mean, it generally decides by itself. Also, you can configure it. We will come back to that once we are discussing the admin. Okay. So this is configurable as well as elastic. It is up to you can leave it to the system. Okay. It will decide on various kinds of things, such as if you have a smaller number of machines, then you will have different sort of chunks and the strategy will be different. Okay. So do not worry about that right now. It does it very smartly. Now let's talk about what is HDFS. We talked about all of this, and out of this, so the sole objective, the design goal of HDFS was distributed file system, a file system which runs on 10,000 computers parallelly to give you a place to store your data without worrying even for a minute that how are you going to store this data and where. You don't have to worry about that. So that is the sole objective of HDFS, providing you a file system which runs on 10,000 or lakhs of computers simultaneously. Okay. And other than that, when you are making a distributed system, you have to take care of these things. First is hardware failure is very common. When we say hardware failure, it means the disk has failed. Disk has got bad sectors and the computer has crashed, OS has crashed, or network wire is gone, or one particular rack is burnt, or a data center is burnt. Those are hardware failures, and HDFS is supposed to handle all of that. Second is streaming data access. As I told you when while giving an example of watching a movie, say you have built a system for say hostel, where one of the guys rent a movie, or one of the guys have just bought lot of movies and put it on this system, and there are thousands of people who are trying to watch it. Same movie, all of them are watching. Now, if it's being streamed from a single machine, then it cannot work out. Ideally, it should be sliced into hundreds of machines, and each machine is having a different section of the movie, and each different node is serving a different piece to the people, and that is what is called streaming data access. So multiple machines is streaming the data to the user without worrying about how to divide the job. So that's the role HDFS plays. And of course, the whole objective was large data set and simple coherency model. Simple coherency model means you stick to the data. I mean, the data stays nearby. Okay. So I'll give you an example. So in a when you are if you have got a similar data which your MapReduce or some other stuff is going to run on it, it is easy to have it in the same rack. Okay, so most of the HDFS is rack aware. Okay, and that gives it a data. I mean, when the data which is going to be used together should be nearby. That is what a simple coherency model is. And other is moving the code is cheaper than moving the data, which of course is this. And third is portable. Okay. Now I'm going to delve a bit into details of HDFS architecture. So I have a half an hour left for me. I'd like to answer your questions. So Jamil's question is, can JobTracker and NameNode be two physical different master nodes? And JobTracker and NameNodes are the same machines, will be there two JVM process, one for NameNode and other for JobTracker. Yes, so they can be different. They are basically daemons running, and you have entitled these two guys, one as JobTracker and other as NameNode. Okay, so they are entitled by you. So either you run it on the same machine or on different machines. It will be, I mean, it's up to you. Now the second question is what Jamil has asked. JobTracker and NameNodes are the same machines, will be two JVM process, one for NameNode and yes, sort of, yes. So since every both of them is a separate Unix process, so they spawn a different JVM. But after JVM 6.0, this booting two JVMs was actually combined by JVM under the hood. Okay, so you are not really spawning different complete different JVM altogether. You can utilize a single one. That is what was done by Java. I mean, the code is still behaved as if it's launching two separate JVMs, and that's how you look at it. But most of the code is shared under the hood by the JVM guys. Okay, that was done in JVM 6.0. Okay, so for you it is like two separate JVMs, but under the hood it's a basically lot of it is shared between the two. So the memory does not go bonkers. So I hope I answered your question, Jamil. It was an interesting question. Now let's talk about HDFS architecture. So I talked about name node and I talked about data nodes. So data nodes are actually the guys who are responsible to store some data, while name nodes are sort of bookkeepers. They keep a record of which file is where, which piece of which file is stored where, and how many replicas are we supposed to keep for this file. Okay, what is the default replica are we going to keep for these files? Is if any of the machine, and all of these machines are being pinged by name node and vice versa. And if any of the machine is going down, name node starts moving that data, or if say one of the machine went down, so name node will figure out that these are the pieces we have lost. Okay, now since we have lost these pieces and this file says that it has to have the replication factor of 3. Replication factor of 3 means there should be at least 3 machines storing this file, or there should be 3 times storage, 3 times 3 copies of the same file should be stored. So now since these pieces have been, this server has gone down and this data, the replication factor has gone down because one piece went away out of 3. So we have only left 2 copies of the same data. Now we want to have one more copy. That is decided by the name node. Okay. So name node is like a bookkeeper of what file is there and what is the replica and everything. While data nodes are the actual guys who are going to store the data. And also one very important thing you have to keep in mind, which we all forget to answer. The reading and writing actually happens from the data node. So you do not write to name node. Name node takes the header information and then redirect you to the write node, saying this is the machine, you go and write to it at this location, and this is the head, this is the position you need to be writing, and just tell this to data node. Okay, so name node, had it been, had name node be reading from data node and giving back to you, then name node will be horribly loaded and will become the bottleneck. Right now the name node's role is given a file, which pieces are lying on which server, that information it gives back to you. And when I say you means the Java driver or any other language driver or file system driver you are going to use. That guy will do the job for you. So the driver, the client driver, which asked the name node for a file. Name node said, this file exists on this IP address, why don't you talk to them? And this is the sequence. And now this driver will talk to each of these nodes and give you back the data. That is the role of the name node. And that is how it works. And the replication keep on happening between these data nodes. And reading, writing, name node is like a head of the orchestra, while rest of the people are the orchestra. They are, name node is not playing any music. It's just acting as the master. So this is roughly the diagram which shows that rack 1 has 3 machines. First machine has these pieces, second machine has these pieces, third machine has these pieces. Now rack 2 has got 2 machines, and 2 machines, when I say these are 2 data nodes, rack 1 has got 3 data nodes, and then there is a singular name node. It's a singular name node, and that is the architecture. Okay, it's exactly the way Google file system was written in the beginning. It's there's a paper on this. Okay, now, so I hope this diagram is clear to you guys. So hope this diagram is clear. Do you have any questions? This is an important diagram. So client is actually writing from the data node here and here. Similarly, client is reading from the data node, and the metadata operations are going all to the name node here. Okay, here. So can I? Okay, if I okay. So this is the name node. Name node is keeping these things and then keep on doing various kinds of operations like replication. Informs data nodes that hey, replicate this data from here to there. Now data node amongst themselves start copying this data from here to there. Name node does not do this, that it will read the data and then write to elsewhere. No, it lets them communicate, and so that name node's job is to keep itself as light as possible. All read write operations should go to the data blocks. Okay, I think nobody has questions, so I will move on. So I talked about name node and data node. Name node is the master of the system, maintains the manage, and data nodes are the actual guys who are storing the data. And this is what happens. This is what goes underneath. A client came, said, I want to write a file. It talks to HDFS. HDFS is nothing but talking to name node. And then name node said, okay, fine, you want to write? I have made a note of the file name. And this is the file size. And why don't you go and store? Why don't you go and write to these nodes? Okay, and these nodes propagated the data, and then you got and then finally it sent a close, and then our job is done. So distributed file system, so client is talking to this distributed file system, which internally is basically storing everything here. Here, when I say distributed file system, it's actually a sort of driver, file driver, whose job is to interact and isolate your Java code from all of these complexities. Okay. Now, this is how a read happens. So this client is saying, I need to read this file from this location to this location. So client can say in both the ways. Client can also tell, I need to read whole file. Client can also say, I want to go this bit of the file and read onwards. Okay, and that communication happens with the name node. Name node gives back the block locations where in the data node it's existing, and then the driver talks to the data node and gives back the file to the HDFS client. This is what goes. Okay, I actually no, I mean fine. So this is supposed to be read here. It is supposed to be read. This is wrong. Okay. Now this is what happens. So Ashish's question is, what is the maximum number of replications can we keep for a single file? Okay. So it is basically, if you see from logic perspective, there is no point in keeping the replications more than number of total hard disks. Okay, if you have replication of a file at 2 locations in the same hard disk, it does not make any sense. So that is generally considered as the upper limit of the replication. Out of all your nodes, if you count all your hard disks, that is the upper limit. Okay, that you should be keeping, because it doesn't make any sense to keep, because hard disk is the minimum unit of the failure. Failure could be on the node level, failure could be on the rack level, and failure could be on the data center level. Okay. So ideally you should just do a rough computation and say this is the maximum number of replications you should be keeping. And instead of doing that, if you have got different data centers, say you have got 3 data centers, and your data is very critical, or I mean, you will have to do a balancing act. How critical is your data? How fast it is being going to be accessed by various kinds of people? So it will be up to you completely. Okay. So maximum number is generally decided by you, decided based on the number of hard disk drive you have. Now next question from Assis is, can we increase number of replications? Can we increase number of replications of single file? Yes, yes. So as you see that when I'm writing a file, I also specify that this is the replica factor I'm planning for this particular file, and so you can update this at a later point of time, and that time it will be the data will be redistributed. Interesting questions. So good questions actually. So I hope I answered your question. So okay. Now let's move on. There are few things you need to know about NameNode. The most of the data at the NameNode level is in the memory. Okay, that's by design to make it really fast. And when you are choosing your NameNode, you should be choosing a machine. You should be choosing a machine which is having a great RAM, and that RAM size will decide how much your cluster can store, how much data can your cluster store. And if your RAM is small, if the RAM of the name node is smaller, so there is a clever trick this guy does, HDFS does. It will create larger size of chunk, larger size of files. Okay, larger chunk size. Why? Because that way it will have to store less data in its memory. Okay, but it's not a good idea. So if you are not deciding or fixing the size of the chunk, then the name node is going to make a bigger sizes if the memory is small. Second, there is no direct there used to be no direct failover of the name node data, but now there is a snapshot failover. So name node looks like this. Okay, name node contains that this is my file, this is part 1, part 2, part 3 of that particular file, and this is my replica size. And where does it exist? Where does it exist? On first machine, third machine, or second machine, fourth machine? So it is that way. Now let's now what I mean, metadata contains your files, block size, data node for each, and then file attributes like when was it accessed and what is the replication factor. So anything you can think of name node is like a file allocation table, FAT. And then it also keeps a transaction log, records of file creation and deletion also. And this is generally stored in the disk. This is generally stored in the disk. Okay, so here we talked about the architecture of name node and data node. Before I move on to job tracker, which is the second part, I would love to answer your questions. Do you have any questions regarding till now, or should I move on? So are you guys with me, or you guys have lost me, or I have lost you? So we talked about how, on a very detailed level as well, how does the distributed file system work? We have two things. One is called name node and other is data node. Name node's duty is to act as the sort of a bookkeeper for you, sort of a librarian for you, while data node's job is to keep the actual data. Okay, great. So I think nobody has a question. I should move on. Feel free to drop me an email or feel free to discuss with me later on if you have any questions. Okay. Now job tracker. Job tracker is basically the guy who is responsible to do the computation for you. Okay. For you, this is a point of contact. So you hand over whatever code you write. Code, when I say code in terms of maps and reduces, you write your code and give it to job tracker. Job tracker takes that and sends it to each machine which is running task tracker. Task trackers are also data nodes. Task trackers are also data nodes because I mean your task is going to also run on the top of data. Okay, and it is very optional for you. Okay, if your task is not having any access to any data, then it's a completely different story altogether. So, but in case of creating your job or MapReduce job, you always tell that this is the location of the data which I'm going to access for this thing, this task. And that's how job tracker, after communicating with the name node, decides that which I mean, how is it going to partition the logic and send it to various task trackers. And task trackers execute your MapReduce job and give it back, give back the results to job tracker, who either takes either return back to the client or starts doing some other processing work. Okay, so in here when we say client, it can be a workflow system, it can be your Java driver, it can be the command line. Okay, so that is how it is. So the actual job is done by these nodes, while the job tracker, sometimes also referred to as launcher box in Hadoop cliche. Okay, people call it launcher box, and acts as a platform from where we are launching the jobs. Okay, so job tracker's job is basically dividing the MapReduce and handing over to the task tracker. Task tracker is the guy who is doing the sorting, who is doing the processing and execution of your logic and giving back the results to the task tracker. This is a pretty simple thing. But if you see under the hood, what is actually doing? User is first copying the input. Say whenever you are defining your MapReduce task, you always mention that this is the file system you are going to use. Okay. Now user talks to the client. User has already put his files onto the DFS, which is Hadoop HDFS, and now user is talking to the client, which is his Java program, and I mean Java program is talking to the DFS, creating splits. I mean, and then I mean client is not creating splits, submits job to the tracker, tracker creates splits. Okay, now after creating splits, it moves on to the next step. Okay, as in
After creating splits, it sends the each split onto the task tracker and gets it executed. And the same thing has been explained here again. Okay. So either way, this is how it works. Okay. So maps and reduces, this is how it works. Any questions related to this right now? Should I go through this diagram once? So here we talked about this, right? Client has created a job and then uploaded a DFS, then whatever job description we have created using, this is the Uzi kind of job. I mean job.jar means it will have your map and reduce class, both classes together, and job.xml will define that this is my map, this is my reduce, these are the files which I'm going to access, and this whole package is your job definition, and it is submitted to the job tracker. Now the next step is that job tracker is trying to figure out what does that whole package means. Jar is equivalent to zip file, okay, which has got one entry point and other standard stuff. Now after picking that zip file or jar file, it figures out that these are the maps and reduces, creates these in memory, compiles it and sends it to the job queue. Job queue internally executes the map reduce and puts back into the results as the job queue, and then gives back the results to the job tracker back. Okay, so this is something which you don't have to worry about in general. This is internal mostly. You don't have to worry at all. When I'm going to show you MapReduce, these are not something to be worried about. You need to worry about. These are automatic. These are completely automatic for you. These are this is how Hadoop functions internally. And this is the further job, okay, whereby each task tracker keeps on informing the job tracker saying I'm done with my job, I'm done with my job, and each slot whichever is allocated to the each task tracker, he fills back into the job queue with the answers. Okay, and job tracker's role is that pick the tasks where data is local only. Okay, this is how it generally functions. So are you guys comfortable with it, or should I describe MapReduce in detail? Actually, I would love to describe MapReduce, but then again, it is going to take at least half an hour. Okay. You can read more about both of these at these places. And the assignment for the next class is, you have to set up a Hadoop environment, because this is the first class, and I mean this is a standard way. So we generally create quizzes in the LMS, and you generally have to go through quizzes so that you know that you have learned all of this. And we give an assignment for each of these classes, which we make it available in our learning management system, also known as LMS. And we will provide you a Hadoop environment based on virtual machines. I mean, in our case, it's both. So we provide a cluster as well as virtual machines, which you can run. If you want the data to be local and you want more experimentation, you can download a virtual machine and run it on your machine, or you can just start using our clusters. So that is pretty much from my side. That is pretty much from my side. And if you have any questions, you can ask right now. So as part of the full course, these are the topics we are going to cover. I'm going to basically go, this is what we have gone through. Hadoop basic architecture we have gone through. We'll address once more whenever need arises. And then we'll go, in the second session, we'll go through the cluster setup. How do you do a cluster setup? And the various project environment, and how do you do the ETL jobs? Okay. How do you take the data from your local to your DFS and vice versa? And we will have a detailed discussions on these 2 days on MapReduce framework and its testing. Then we will have one whole class for dedicated for Pig and Hive. And then we talk about something called NoSQL databases and HBase. And in the 8th class, we talk about 3 things in a single shot. One is Zookeeper, other is Uzi, and other is Mahout. Okay, because these are not, we don't need to go into very high details on these 3 things. We will finish in single day. Then these 2 data import techniques we'll talk on the 9th day, and on the 10th day we will talk about big data sets and how can we use those big data sets for our project assignment. And also we'll talk about the recent changes in and recent features of Yarn. Okay, we've got a question. So basically, Vishnu is saying that it has helped him a lot. Thank you very much, Vishnu. And I am also very honored. So Amit is saying that he has got no questions right now. It was very knowledgeable for him. And Ashish, do you have any questions right now, or should we call it a day? So feel free, guys, feel free to ask me questions. Okay. And if you want to continue, you can buy the course. And if you have got a referral discount, okay, if you have got a referral discount, or you have got a any other refund, we will send it back to your accounts. Do not worry about that. Okay, so you can continue with your purchase. Okay, you can continue with your purchase if you want to go for the full course. And if you have any questions related to any of these topics, feel free to talk to me. Feel free to talk to me. My email ID is listed there, and my phone number is here. You can make a note of my phone number. Okay. And also, I mean, if you are going for real class, I will basically help you. I'll basically help you with respect to LMS also, the various points at LMS. How do you access it and what are the features of it? Okay. LMS is learning management system. So feel free to drop me an email or at this ID, or call me at 9591 953899. Okay. This is my phone number. You can call me at this number. Okay. And this is my email ID. Feel free to call me at this. Okay. Sandeep at nobigdata.com, and our website is there. You can have a look at the website also. Nobigdata.com, KNOW bigdata.com. Okay. So that's pretty much from my side. Thank you, Assis. I'm actually happy that so many people came today, and it was great meeting you all guys. And feel free to get in touch. And if you really like it, go forward. And I mean, if you want, you can go forward with the full course. Good night, guys, from my side. And if you have any questions, stay in touch. Okay. Even if you are not going forward with the course, now stay in touch because we will have free seminars on other big data technologies as well, such as data sciences and Mahout and programming in R, analytics in R, and couple of more front end technologies free session. Okay. Thank you, Ashish. Good night then. Good night, Ashish. Okay, great. I've got a good question.
I have one quick question about map and reduce slots. What kind of relationship exists between slots, map tasks, data splits, mapper and reducers?
So let me just give it a thought again. What kind of relationship exists between slots, map tasks, data splits, and mapper and reducers? So, I mean, map tasks are basically mappers. Okay. And I mean, whenever each of the map task is basically instance of the mapper logic you have written, and similar is your reducer way. The thing is, data split happens in such a way that the place your code is going to get executed, the data has to be near that. Okay. And similarly, in the same fashion, the slots are allocated to you. So it should not be that your code is getting executed on some machine and the data is lying somewhere else. So that is the role being played by the task executor, job executor. Okay, job executor makes sure that your data split is very closer to the data split happen in a way that the task execution happens on the same place where the data is stored. And that is how it works. So if you are doing a map job and it's reading a lot of data, so it will be sent to various places and the data at that place will be given to your mapper job. If there is a 10th machine which does not have any data for your kind of job, the file which your map is trying to access, then your map job will rarely go to that machine. It will only happen in unexceptional circumstances. Okay. So that is the relation which exists between these things, all these slots. So mapper, the when you define mapper, you define that this is the file you are going to need, and based on that file it is decided that your mapper is going to get executed only on those nodes where this file exists. Okay, so that is the relation between your mapper task and data splits as well as slots. Thank you, Jamil. I am honored. I got a great questions from you and looking forward to further interactions. Good night, guys. Good night, Anurag. Good night, Ashish. Okay. So you can actually, I mean, you can actually go to the website and start buying and buy it. In case you are interested, you can go to Hadoop and then there you see this enroll now. and then you can buy. You can choose the price which you wish and enroll now, and then you see this screen. Okay. Okay. So this is how you can go ahead, and I mean, in case there is a referral discount you're getting, you can have this. Also, if in case you are not, in case some of your friends are not able to attend today, there is a session tomorrow, and on 12th you can sign up. Okay. Thank you, Kamal. Good night. And yeah, for sure, I would love to have the discussion further, and let's see if it is useful to you. Good night, Jamil. Yes, sure. It will be available in the LMS. Okay, in the learning management system. Okay, once we create your account, it will be available there. And in case you're not going for full course, let me know. I'll make it available to you. You have my email ID. Thank you, Piyush. Good night. And if you have further questions, feel free to get in touch with me. So Jamil, I will not be making it public. You can let me know. I'll send it to you personally, and I'll be sending this recording to you as well in the email. Good night, guys. Good night, guys. I'll just hang up now. Feel free to ask me a question in case you have any question, or I'll say goodbye now. And drop me an email in case of any doubt.